Hey everybody, this video is going to discuss acceleration. So by the end of this, you'll be able to recite the equations and related units of measure of objects moving with acceleration. Add these notes to your existing notebook. Let's get going. We've discussed scalars and vectors, speed and velocity, and distance and displacement so far in this unit. We've talked about the meaning of slope on a position versus time graph. Today we're discussing things that are moving with changing speeds, which is another word. That's another way of saying acceleration. If something's speeding up or slowing down, changing speeds. So what kind of motion results in acceleration? If you're changing your speed, you're accelerating. If there's a change in direction, you're accelerating, even if the speed stays the same. That's a weird one. And if there's a change in both speed and direction, there'd be an acceleration. So let's do a few examples here. Shown below is a toy car moving along the track. The motion of the car is shown with a series of snapshots taken at 1-second intervals. The green arrows indicate the velocity of the car at each instance. And it says velocity specifically, which means magnitude and direction. The longer the arrow, the greater the speed. In other words, at A, it looks like its speed is less, and at C, it's about the same as A, but B looks bigger, so it's moving faster in terms of speed. It says, on which sections of the track does the car accelerate? So if we look between A and B, its speed is increasing, and its direction is slightly changing. Then from B to C, the arrow is getting smaller and smaller, and it's going up the hill instead. So it's accelerating at section A, and it's accelerating at section C. We can see it looks like during part B here, the arrows are staying the same length, and the car's moving in the same direction, so it's not accelerating during that time. In other words, it speeds up as it goes down the hill, then it slows down as it goes up the hill. During A and C, it accelerates. Average acceleration is a vector, just like displacement and velocity. It's defined as the change in velocity divided by the change in time. And here's the average acceleration equation. So just like we did with displacement, to find the change in velocity, we're going to do the final minus the initial velocity. The units are meters per second squared, or it's another way of saying meters per second per second. For things that are undergoing constant acceleration, there's 4 different equations we're going to use, and we'll go over in class how to actually decide which one of these applies to each situation, but here's the main 4 equations. For all these things, VI is always the initial velocity, VF is always the final velocity, A stands for acceleration, D stands for distance, or displacement, depending on the problem, and T stands for time. And for all these quantities, the units for distance are meters, velocity is always measured in meters per second, acceleration is always measured in meters per second squared, and time is always in seconds. So we've talked about position or distance versus time graphs. We're also going to see velocity versus time graphs. And these we get units of meters per second squared usually, because you have velocity, which is meters per second, versus time, which is seconds. This also means that the slope on a velocity versus time graph tells us acceleration. Shown at the right are velocity time graphs for 2 different cars, A and B. Is the acceleration of car A greater than, less than, or equal to the acceleration of B? So according to the previous slide, the slope of a velocity versus time graph tells us the acceleration. So which one of these has a steeper slope? That would be the one that has a greater acceleration. If you pick B, you'd be correct. Since B has a steeper slope, it's accelerating faster than A. Thanks for watching. Make sure to answer the questions in Schoology. Bring your notes with you in the next class to help on the note quiz. Thanks for watching.